Okay. Is it recording? Hold on. Okay. Okay. So from here, as I said, I highly recommend you all to do this because now I just need to find my I flange. Okay. Even for bending moment, it's the same thing. Okay. 12, 3 cube divided by 12 plus by 36. Okay. I'm not even thinking now. Okay. Minus 1.5 squared. Okay. So this will be equal to 12 times 3 power 3 divided by 12 plus by 36 times by 3.3 minus 1.5 close bracket squared is 143.64. I will do it again. 12 times 3 power 3 divided by 12 plus by 36 bracket 3.3 minus 1.5 squared 143.64. Then we will do I web is equal to 4 6 cube 12 plus by 24 3.3 minus by 6 squared. Okay. 4 times 6 power 3 divided by 12 plus 24 times by 3.3 minus 6 close bracket squared is equal to 246.96 inches to power 4. Okay. So I'll do it again. Hey, my calculator gave me an error. 3.3 minus 6 squared. 246.96. Okay, so I total is equal to 143.64 plus 246.96. 390.6 inch to power 4. So in a test, what will happen if you do it this way? I will give you mark. So over here is 1 mark. Over here is another mark. Okay. So that's how I mark. That's why it's important that you break it up. Okay. In your calculation, it will have less error. I can give you part mark easier this way. Okay. Now, if you look at the solution, I don't know whether it's right or wrong. 390.6, 3.3, 390.6. If you look at the solution, okay, we were bang on. Okay, we were exactly. Don't lump everything like this. It can be very confusing. Okay. Okay. So the question asks us to determine the shear stress. Okay. So the maximum shear stress will be at the centroid. So we are aware that the centroid is 3.3. So it's somewhere around here. So this is 3 for 3.3. So that is our ZZ. Okay. So that is now our ZZ. We are aware of that. And we also know that the distance from here to here is 3.3. If you were to deal from the bottom, the distance from here to there is 5.7. Okay. So there are 2 ways that we can do this, okay, which I want you all to be really, really comfortable with. So we can analyze from the top or from the bottom. Okay, so I call this section above the center at the top, the one below at the bottom. Okay, so let's start from to me, the easier one is from the bottom because the thickness is uniform. Okay, let's start. Let's find Q max from bottom. Or with bottom, whatever you call it, with bottom or bottom. So the formula is width, depth, y bar. Okay. So the width we know is 4 inches. The depth is 5.7. The y bar is 5.7 divided by 2. So 4 times by 5.7 times by 5.7 divided by 2 is equal to 64.98. Okay, 64.98 inches to power 3. Okay, now let's do the top. Okay, so Q max by looking at the top. Okay, so we have to find the Q of the flange plus by Q of the web. If it's done correctly, the answer should be the same. Okay, so width is 12, depth is 3, y bar is 3.3 minus by 3 divided by 2, right? And then plus by the web. So the web is the width is 4, the depth is 0.3, right? Because this distance from here to here is 0.3, and then this is equal to the y bar is 0.3 divided by 2. Okay, so this will be equal to 3.3. 3.3 minus by 3 over 2 times 12 times 3 is equal to 64.8 plus 4 times by 3 times by 3 divided by 2, 0.18. So it's equal to 64.8 plus 0.18 is equal to 64.98. Exactly the same, right? So definitely I will choose this. Okay, I will choose that way of finding your y bar or your Q max. Okay, so quick. Okay, and why this is true, why either you take from top or bottom is the same, because of rule number 4 that the Q, the first moment of area cannot cross the centroid. Okay, so from here for both, yes.
Sorry to interrupt you, Gene. You have a question in the chat.
Oh, okay, I did not see that. In what situation is the Q max? So Q max will always occur at the centroid. Okay, May Shao Tai Q max will always be at the centroid. Okay, because is at that line at the centroid, either from the top or the bottom, the cross sectional area will be its biggest. Okay, or the Q max will be its largest. Okay, the first moment of area. Does that answer your question?
Yeah, but like, so like why the bottom is always equal to the top one?
Because why? Because at the centroid, the cross sectional area, okay, the area happened to be exactly at the center. At the centroid means the top cross sectional area and the bottom cross sectional area are balanced, are equal.
All right, I got that. So
Okay? That's why it's called the centroid, right?
okay, yeah.
Okay. So from here, we now know that tau max is equal to Vy over Izz Qz divided by T. So this will be equal to Vy. Okay, given our Vy to be equal to 12 times 10 to the power 3. Qz is equal to, or Q about the z-axis is equal to 64.98. Either you take from the top or the bottom, it's going to be 64.98. Izz is 390.6. And then the thickness we know is 4 inches. Okay, so 12 power 3 times 64.98 divided by 390.6 divided by 4 is equal to 12 power 3 times 64.98 divided by 390.6 divided by 4 is equal to 499.078 ESI. Okay, let me do it again. 12 power 3 times 4 499.078 ounce per square inch. Now I want to do something further. Okay, and I want to determine. Okay, what we are going to do is we're going to determine the shear stress distribution equation. Okay. So we are going to deal with the top first. Okay. So we are going to deal. So if this is our, I'm going to draw our centroid. Okay. So if the green is our centroid. Okay. So it asks us to determine the shear stress distribution. Okay. So we are. So this is above the centroid, right, at the top. So we know that the distance from here to here is 3.3, right, inches. So we are going to determine 0.3 y to 3.3 inches. Okay. So why we consider this? Okay, so the range. So this is 3.3. This is where our 0.3 is. Okay, why we pick that range? Because we're going to form piecewise equation. Why we pick that? Because the thickness is constant as 12 inches. Okay, the thickness is constant. So we now, all we need to do is to find our Q, right? So the width is fixed, right? Width is 12. Now the thickness varies. So it's 3.3 minus by y. So your y, this is your y, right? If we want to find, or if we go to determine this area, this defined area, and some of you will ask me why the defined area starts from the distance furthest away, because this is your analysis direction. Okay. So this distance from here to here is 3.3 minus y. Okay, so this is your width, this is your depth, and the y bar is just 3.3 plus y multiplied by half. And this over here is your y bar. Okay, so this will come out to be equal to 3.3 times 3.3 times 12 times 0.5 is equal to 65.34 minus, wait, I'll do it, 12 times 0.5 times 3.3 times 3.3. 6, yep, so 12 times 0.5. So this is 6 minus 6 y squared. Okay, so that is your first moment of area as a function of y. Okay, let me write this down. Q as a function of y. Okay, so how do you know that this is correct? How do you know that this is correct? Okay, if you substitute y is equal to 3.3, the whole equation over here, okay, Q at 3.3 must be equal to 0. Okay, so 65.34 minus 6 times by 3.3 squared is equal to 0, right? Okay, that's how you can check whether is it right or wrong. So from here, you know that your shear stress distribution as a function of y will be equal to 12 times 10 to the power 3 divided by 390.6. The thickness is constant at 12, as you can see down here. And this will be equal to 65.34 minus by 6y squared. Okay. So this will equal to 12 power 3 times by 65.34 divided by 390.6 divided by 12 is equal to 167.281 minus 12 power 3 times by 6 divided by 390.6 divided by 12, 15.361. 15.361 y squared. Let me do it again. 12 power 3 times 65.34 divided by 390.6 divided by 12. 167.281. 12 power 3 times 6 divided by 390.6 divided by 12 is equal to 15.361. Again, how do you know that this is correct? If you substitute y